My name is Galagash, and I will be taking you through the derivation of the Blasius equation. And there are so many ways to do that, but we want to derive the Blasius equation using the boundary layers. Of course, this high-level mathematics is advanced for, especially in the field of advanced fluid mechanics, for those pursuing either their master's or maybe PhD in applied mathematics. Let's look at this Blasius equation. I want to believe you have also come across the flat plate boundary layers, in which we have some openings, a kind of a stream that is parallel to the plate, and then we have a streamline flow. You either have a streamline flow or maybe a laminar flow. So with that, we are going to assume some characteristics like 2-dimension. We can take laminar boundary layers. We can also take maybe semi-infinite plate that holds the parallel plate. We can also assume that this plate is steady flow and it is incompressible. And having assumed that, we can now use very quickly these boundary layers to assume and find our equation for Blas, which will give you the solution. So I can start by the continuity equation. So if I have, if I take partial u, partial x, and I add partial v, partial y, and then I take this to be equal to 0. What this tells you is that we can have our partial u, partial t, partial u, partial t, plus u, partial u, partial x. Then we add v, partial u, partial y. So this must be equal to these boundary layers, which is 1 over p. We can take this to be partial p, multiply that, so it is partial p, partial x. Then we add this to v, this now partial squared y over partial y squared. So this is what you now have. But again, for a flat plate, as y approaches infinity, as y tends to infinity, what you observe usually is that partial p, partial y is equal to 0. So if y approaches infinity and partial p, partial y is 0, then what this tells you is that u is equal to u infinity. It is equal to u infinity. So when I say that we have partial p, partial y to be equal to 0, again, this takes you to u infinity. So if u is u infinity and partial p, partial y is 0, then this implies that our u infinity is constant. So it is constant. There's a lot of combination that will be going on here, but if you pay attention, you will get the process of deriving these Blasius equations. Because again, pressure in a fresh stream is constant, and by our equation that we have here, this equation, partial p, partial y equals 0, what it means is that the pressure in fresh stream is constant. And if it is constant, by the virtue of that equation, the same distribution get impacted or get imposed on the boundary layer. So there are some assumptions that we must make now. And this assumption is done in order to obtain a similarity solution. So I will make some assumption. And one of the assumptions that I will have to make is that I will take neta. This is neta. So if I take neta, I will say that my neta is equals to maybe y over maybe partial x. This is the first assumption. The second assumption is that I will take my u over maybe u infinity, and this must be equals to maybe h over neta. And if this is true, this implies that my u therefore is equals to v infinity, then h all over neta. And I have said it is done in order to obtain similarity solution. I'm trying, there are a couple of ways, there are so many ways you can derive these equations, but I will give you the, I think, one of those ways that you can find easy. I'm not sure it is that easy, but then there is no other way. So now, we can bring in the stream functions, and the stream function we are going to bring is psi. This is psi. So if I bring in psi, we know all this psi that we want to bring is simply going to give us it is an arbitrary function. So if I bring in psi, it would help me to look at the continuity equation. So psi would satisfy the continuity equation. So I would write this equation now in terms of psi. So I will have u to be equals to partial psi all over partial y. And I will have v to be equals to negative partial psi all over partial x. So if this is the case, our partial psi over partial y will be equals to u infinity h into neta. So psi, therefore, solving for psi, we will have to integrate both sides. So if I integrate both sides, I will simply have u infinity, the integral from 0 to neta, of h d, that is partial y, plus maybe one constant arbitrary function k of x. So this gives me my psi to be equals to v infinity partial x, the integral from 0 to neta of h d neta. So this is d neta plus kx. So you can keep this in one side. So now we can now check on because we know by boundary layers for flat plate, even the wall is streamline. And when we say streamline, we simply mean that there is no flow. It can't allow flow. So if that is the case here, we will have ut in terms of y. So if I take the boundary layer, I will take y to be equal to 0. And psi as well to be equal to 0. So if I take y equals 0 and psi equals 0, since we know that we know that y is 0 and psi is 0, so f of 0 is 0. So this implies that our constant, which is kx, is equal to 0. So our psi, therefore, is going to be equal to u infinity. Then we have our partial x and a function of neta. So you can have this. So we continue from there. So this is where we are. You can just leave this way. Because we need to know that psi is u infinity partial x f infinity. But we know that u is equal to partial psi all over partial x, partial y. We know that. So we can now substitute this value that we got earlier here, u infinity, we substitute in psi, such that we will now have, if I substitute that, I will now have our psi. In that case, our psi is simply going to be u infinity. Remember, we have psi u infinity, then partial x. So I will now put my partial x and then put my f as a function of x. So the whole of this that we have here, we can now multiply by partial over partial y. So we now have that. So what you should observe here is that if I have u to be u infinity like we had earlier, and we had also seen this is a multiple of partial x, and we have now f as a function of x, but in this case we will put partial neta over partial y. So what this is telling you here is that f, which is a function, this f, which is a function, is simply d over d neta. And the whole of what we have here, which is partial neta over partial y, is nothing but 1 over partial x. So if this is 1 over partial x, and this function is d over d neta, so we will simply have u to be equals to u infinity, this f, and we have seen this is 1 over partial x, so this is d neta. So since they are multiple of each other, this becomes simply f prime, the first derivative of that. So you can have this. Now that we have what is u, what is going to be v, we saw earlier on when we were here, we had started looking at this and we see psi. We also see v. So this partial u partial t. Then we have u del x, and then we have v del u del y. So our v therefore is going to be negative if I write in terms of psi, partial psi all over partial x. So v is going to be negative partial. If I try to have partial in terms of partial x, and I put my u infinity partial x as a function of neta. So this is a function of neta. So therefore, v is negative u infinity, negative u infinity. So I will have a function of neta. Then I will have 2 partial of x in respect to y, partial x, plus partial x. Multiply this by the first derivative f function, then multiply this by neta over partial x. But what here? Look here. You can see partial neta over partial x here. What this tells you is that partial neta over partial x is nothing but partial over partial x. This can be multiple of y into partial x. And this partial x y over partial x is nothing but, this is nothing but negative y over, so negative y over partial x squared. So we can now write our general v, since we know that this partial neta partial x gives us partial x into y partial x, which is negative y partial x squared. So our v therefore, we start with v. So our v is going to be, our v therefore is going to be negative u infinity. Then we have f, which is a function of neta. Multiply this by derivative d, then partial x, all this by dx. Then we add partial x, a function, the first derivative of f, multiply this by what we have here, which is now negative y over partial x squared. Negative y over partial x squared. Then multiply this by d partial over partial x. We can do some simplification and maybe cancel out so that we get our general v. So v is going to be negative u infinity. We have f, which is a function of neta. And then we had d partial over partial x. Plus we also have partial f prime. Multiply this by, we have another neta, so negative neta over partial. Which other one is there? You have d neta, d then partial over partial x. So here we have partial here and partial here. So this partial can go with this partial, such that we will have our v to be equals to negative u infinity v partial over partial x. Then we have f as a function of neta, then minus, this is neta, then minus neta, this is a function with f prime of neta. So this is our v. Simply keep this. Then we proceed. So the next thing that we want to ask ourselves in order to get the general Blasius equation is we need to know what is partial u, partial x, because remember we started with looking at partial u, partial x, and we started with this continuity equation. So we want to rewrite them and substitute back into the x direction of the streamline flow in the boundary condition, which in this case will be the momentum equation. So this is what we have. So let's do that. You can take this up. So this is where we are. We have what is v. So now we want to look at, we want to first of all find partial u, partial x. Partial u, partial x is nothing but partial x is a multiple of u infinity. So we have u infinity of the first derivative f prime. So this is nothing but u infinity, the second derivative f double prime of partial y over partial x, which will give us negative u infinity f double prime of neta. And this neta is moving along a streamline flow, so we divide it by epsilon. Then we multiply this by d partial over partial x. So that's what we have in terms of partial u, partial x. The next is to look at what will be now partial u, partial y. Partial u, partial y is going to be like we have partial x, so we simply have partial y in terms of u infinity, f, the first derivative of that function, f prime, and this again gives us u infinity of the second derivative, f double prime, just like we have here, and then we will have now partial neta, not the way we have here. By the way, this is supposed to be partial neta. It happens once in a while. So you have partial neta over partial y. And this gives me u infinity. The difference here, we have negative u infinity. Here, this is u infinity f double prime of 1 over partial. We proceed from there to look for now the second partial derivative. So we'll have partial squared u over partial y squared. So what is that? This becomes partial over partial y. Then we have this can be a multiple of u infinity over partial, multiply this by the second derivative. So this gives me u infinity over partial, multiply it. Now this is the second, so we will have the third. So it is multiplied by f triple prime. This can be multiplied by partial neta over partial y. This is equal to, by simplification, u infinity over partial squared, multiply this by the third derivative, f triple prime. So now we can substitute all of these back into the momentum equation. If I do that, I will simply have partial u by t plus u partial x plus v partial u partial y plus partial p in respect to x, which gives me we have my p and neta. Remember, we are looking at this partial u partial t. We have v u into partial u partial x plus v partial u partial y. Then I had 1 over p delta x, then v delta squared y delta y squared. So I have it here. So that all can be, it is neta, that is 1 in terms of p, then partial squared u all over partial y squared. So we can do some cancel out. The steady flow here, in this case we have the steady flow, we can impose from the free flow region. So if I impose from the free flow region, the steady flow, then this cancels out and this also cancels out. So that implies that I will have u partial u, which is this, in respect to partial x, plus v partial u in respect to partial y. This gives me mu. So this is mu. Now this is mu. So this gives me mu. I can write it as mu in terms of p partial squared u in respect to partial y squared. Can factor out u and simplify. I'll have u partial u. Just a minute. If I factor out u, like I said, I have negative u infinity, then f double prime neta of our partial derivative, multiply this by d partial over dx. I add this up with u infinity, d partial derivative of partial x, which is dx now, which is a multiple of neta f prime minus f as a function. Then I can multiply this by u infinity of f double prime, divide this by partial derivative. So this will give me v u infinity over partial squared now f triple prime. There are things that we can cancel out here. If you look at, we have u infinity. So we have this u infinity f prime here, such that if you go back a bit, we could look at it in terms of u as a function, and then we have negative u infinity f double prime. I want to make sure I have not omitted any step. Negative, that is, divide this by partial. Then we have partial delta over dx. Then we add this with v, and our v was what? U infinity f double prime of 1 over partial derivative, which we got as v u infinity over second, that is partial squared, f triple prime. So when we have all this and simplify, we get this, such that we can cancel partial infinity, this u infinity, and then it is, we have also neta over partial derivative, and then we have also here neta f prime, and then we have v u infinity. So this goes with this, and then we have this going with that. And if we simplify now, we will simply have negative d partial derivative of dx f, then f double prime u infinity over partial derivative. This gives me v f double prime, actually triple prime by simplification, then divide this by partial squared. So what is going to be our final in terms of constant that we had already assumed? We'll have f triple prime plus d partial derivative vx, multiply this by partial, then we have u infinity over v, then f double prime to be equal to 0. So from here we can now use this to have a proper ODE, ordinary differential equations, that we can easily understand. So we can let u infinity over v and partial, then d partial over dx to be equal to 1. If that is the case, it implies that partial d partial over dx is equals to v over u infinity. And this is ordinary differential equations. Now you can simply differentiate this. You have 1 over 2 d dx of this becomes partial squared, and this gives me v over u infinity. So what would be the final Blasius equation? The final Blasius equation, therefore, is we have partial squared, divide this by 2, we will get Vx over u infinity plus a constant c. And to avoid a singular solution at some point where x equals 0, we will simply let epsilon to be equal to the square root of 2v over u infinity, the square root of this. So d, actually partial over x, will be equal to the square root of 2v over u infinity in terms of this x direction, and this is equal to the square root of 2 over rex. So this is called, what you have here is called the result of consistent with order of magnitude analysis. So this is the result of consistent with order of magnitude analysis. So finally, we are going to have f triple prime that we already got plus f double prime to be equal to 0. And this is the Blasius equation. So Blasius equation is nonlinear ODE solved by a numerical method. And this is how you are able to derive the Blasius equation for those in their advanced mathematics and engineering courses. Go through it again and follow the steps, and you will be able to understand what is going on. Remain your friend, Sir Galagash.